second. Let's review exactly that. So we talked about characteristic functions. I just want to make sure everybody's on the same page. So what's a characteristic function? F is equal to chi e, the indicator function of some measurable set. E is measurable. Okay. Then we had simple functions. So characteristic functions, simple functions. Right, finite linear combinations. Finite linear combinations of characteristic functions. And then we talked about also step functions, which are less for they're less for Lebesgue integration and more for feeling grounded in Riemannian integration, to compare to Riemannian integration, which is functions that are finite linear combinations of rectangles. So the reason I say this is closer to Riemannian is rectangles, that's still breaking up the x-axis. What we're interested in is breaking up the y-axis, which is why these simple functions are more amenable to Lebesgue integration, to the study. But nevertheless, we still want to understand how the old picture fits in to the new picture. And we proved three things. Anything else I want to say? No. So we proved that given f measurable, there exists a sequence pk of simple functions with increasing absolute values and phi k converging to f pointwise.
K plus 1?
Thank you very much. Converging to f pointwise. This was theorem 1. This is proved 1. And we also proved given f measurable. Do we have a notation for measurable functions? Curly m, which I'm about to use for an abstract sigma algebra, but that's okay. Yeah, okay. Given there exist step functions, pk step functions, which converge to f not at every single point, but for almost everywhere, for almost every point. Anything else I want to say about that? Now, Charlie asked, in this definition, when we proved this convergence of simple functions, we broke up the y-axis. So, recall proof of 1. We broke up the y-axis. Here's my pictorial representation of what's going on. So here's Qn, this like minus n over 2 to n over 2 ball about the origin. First, we chopped off the function to be 0 outside of there. So we're creating these simple functions. And then we chopped off the function to be at most n at this height. And then we chopped it into pieces. Each piece had width in the y variable of 1 over m. So there were nm of them, ranging from L over m to L over m, and I forget where I put the close sign and open sign. You have to be a little careful to make sure you don't cut off the tip when you're doing this. So whatever the function was, we cut it into little pieces depending on where it fell into that range. These were the E. These were the ELMs sets. I'm just reminding you the rough idea of the proof.
So why choose L between 0 and multiple n?
So 0 is here, that first interval.
Yes.
So L ranged from 0 to nm, and then I guess I had some other definition for what you do at the end. So this was just chopping up. N is some integer, I'm chopping it up into nm pieces so that the width is 1 over m, and I'm going from a range from 0 to capital M. This was when f itself was non-negative. So we had some non-negative function, and we're making these step approximations to it. Okay, when you change, so we want to send kind of both n and m to infinity. When you change when you change m, let's say, from m to m plus 1, you've completely changed the regions where the function gets captured. You've completely changed how you're decomposing the y-axis to make your new function. We had these approximating functions, f and m, which were the straightening out of f along the bottoms of each of these intervals, right? And so the idea was, to get your phi k, what you should do is take f sub 2 to the k, 2 to the k. Now this 2 to the k is very easy to justify. Why not just take a further dyadic subdivision of the interval every time, so that whatever the previous decomposition was, the next decomposition either keeps it where it was or only moves it up by 1 over 2 to the k, so that there's no question about the monotonicity. This monotonicity that we were trying to force, which will be useful when we start proving things like the monotone convergence theorem and dominated convergence and approximating measurable functions by step functions so that we can integrate. By simple functions, so we can libate. We could do it by step functions too. Right. Why this one 2 to the k? Is there a good reason for every time jumping this height by doubling? If that grew by 1, it would still get subdivided. So it's just to make some. This one is just to make some nice sequence. This one you really want 2 to the k. Because you want to further subdivide and not worry about if you change m to m plus 1, then it doesn't respect the previous decomposition that you had.
So I see why 2 to the k works, and I think pretty obviously like b to the k would work for any integer b. Maybe not.
Here.
Yeah, but what other sequences could you pick?
I mean, anything as long as whatever your new decomposition is respects the previous decomposition. All you want to do is a further refinement and not a new decomposition, not a new truncation where you have to worry about why didn't the value accidentally go down in this new cutoff.
I guess I'm wondering, like, is b to the k the only one that does that?
That's an even decomposition. That has the same length the whole way.
Yeah.
You could just as well take any partition, just like in Riemannian integration. You don't have to take 1 over n's. You can take any partition and then take any sequence of partitions with mesh going to 0, height going to infinity, with the property that whatever the next partition is, it's a refinement of the previous one.
Right.
So this accomplishes that without hard work. Without saying what I just said, which isn't that hard. It's just a further partition. Okay. Bless you. Is that, that's where we stopped, right? I believe that's where we stopped. Okay, so let's get to some new stuff. Let me slide this. New stuff. So let's talk about Littlewood's 3 principles. So Littlewood's principles. Littlewood's principles. People were not entirely, people were used to things like open-closed sets, continuous functions, and then Lebesgue integration just hit them like a ton of bricks, and what are you supposed to do now? And Littlewood says, don't worry, it's just like it was before. It looks fancy and new, but actually it's all the same. So here are the 3, this is conceptual principles. These aren't, there are precise theorems that go along with them. But just philosophically, principle 1 is that, at least in R, every set is nearly a finite union of intervals. So every measurable set is nearly a union of a finite union of intervals. Finite union of intervals. Okay, why is that true? This is in R, so we can speak of intervals. Yeah?
To be measurable means you can take an open set, a sequence of open sets which are decreasing, such that the measure of the open set will move the set below to zero. Since every open set can be written as you have countable many, at least counting many open sets, you can keep it.
Beautiful. Okay, so the idea of this principle is that basically measurable sets are pretty close to open sets, and open sets are intervals. And well, they're countable unions, but if you drop a little bit here and there, you can make it a finite union. You can approximate in various ways that idea. Let's do some things that are less perhaps familiar. So every measurable function is nearly continuous. Every measurable function is nearly continuous. And the last principle is, so this tells you what happens to functions. Functions are, again, I have to specify precisely what I mean by the word nearly. Most functions are continuous. Well, most functions look like, well, functions are sequences of step functions or limits of step functions. And step functions are flat on E at least, or, step functions are linear combinations of rectangles. So they're definitely continuous inside the rectangles, and there's only finitely many rectangles. I'll show you the argument. The third principle is that when you have sequences, every convergent sequence is nearly uniformly convergent. Uniformly so. So these are three principles. These are not statements of theorems, although they will turn into statement theorems in a minute, of making these principles precise. When you have convergent sequences, if you're trying to prove something and it would really help if the sequence was uniformly convergent, not just convergent, you can do that with a small loss. If you had some arbitrary measurable function and it would really help if that function was continuous, you can do that with a small loss. Okay, that's what these principles are trying to get at. And towards 3, let's prove Egorov's theorem. Question?
A question about the first one.
Yes?
So is nearly a finite union. Does there exist a in 0, 1? Does there exist a subset which is dense and has measure 1/2?
Dense and has measure 1/2. Well, you can take the rationals, and that has measure 0. If you thicken them a lot, you'll get all the reals, and that has measure 1. And if you control how much you thicken them to the point where they have an arbitrary measure between.
So how would you cover that with finite union? Or is it is there some theorem which says that?
Well, so it's not that you're covering perfectly, it's the word nearly is what's vague here. And because your measure is 1/2, well, so whatever intervals you're covering, their lengths have to add up to, if there's infinitely many, the lengths of the intervals have to add up to 1/2, which means the tail is small, which means you throw away all but finitely many, and you get something that's very close to the size of the set. So that's always the kind of argument we have in mind here. Throw away, there's epsilons. It's not with measure 0. It's not up to measure 0. It's up to measure epsilon. Okay, good. Let's do. Was there another question? Yes?
Sorry, what does it say on the third line?
Every convergent sequence is nearly uniformly so. Why is it looking so? Did it used to look better?
Yeah.
Is that better?
A little bit.
Little bit. Every little bit helps, unfortunately. All right, let's prove Egorov's theorem. So, say we have a measurable sequence. So this is a sequence of measurable functions. On E, real valued, with the measure of E finite. Okay, so Fk is a sequence of measurable functions on some measurable set E with finite measure. Assume that for almost every x in E, Fk of x converges to something. So this is a sequence. I want this sequence to converge. And I'll call that F. Okay? Then, for every epsilon, there exists a set A epsilon, which is a closed subset of E, having almost the measure that we want, and on which, and with this convergence, Fk converging to F uniformly on A epsilon. Okay? So once again, Egorov's theorem says, if you have a sequence of measurable functions on some set E of finite measure, now, if your set E has infinite measure, maybe you can chop it off, right? And let's assume that for almost every, I mean, this is very quickly equivalent to, let's just say, for every x in E, because we can throw away a set of measure 0 anyway. Assume that for almost every x in E, this is so hard to read.
Too bright, it's just
It's
blurry.
just too bright.
Why is it so blurry?
Maybe you turn off the light.
Turn off the light?
I think.
Does that make it better or worse?
Doesn't matter.
That makes no difference, right? It's equally bad. All right, let me not mess around with it now. But even zooming in is not helping. Is it something about the angle?
For some reason, the left side is like a lot easier.
Yeah, the left side is fine.
You
and
can
the
just
right
scoot
side-
the paper a little to the left.
I see, but then you can't see what's.
It's always some part of it is so bright.
Maybe we need to clean the lens.
That's gonna help.
that make it worse.
It's a little better. All right. Anyway, moving on. If you can't read, that's bad. We'll work with it. Fk is a sequence of measurable functions on E with finite measure. Assume there's for almost every point this converges to some function f. Then for any epsilon, we can find a closed subset of E having almost the full measure, with this convergence being not just convergence but uniform convergence on this closed subset. Let's prove it. Slide up a little bit more. Okay, Egorov's there. All right. The first comment is enough to assume. That's what we said a second ago. Enough to assume that Fk goes to F for every x in E. Okay, so throw away your set of measure 0 from E just to begin with. It's not going to change anything else. Now, for each n and k, for each n and k integers, I'm going to try to write bigger. Let's see if writing bigger makes it better. Bigger is better. E n k. That's
great.
Well, that's on the left
Left
side.
side.
Yeah, the left side's always good. Is equal to the set of x in E. I want to catch the condition that the jth function differs from the limiting function f by at most 1 over n for every j after k. Let's process this. And let's see how it looks. It doesn't look any better. Does it look better?
Yeah.
Okay.
To read though.
Okay, it's easier to read. All right, I'll try to keep it big.
You want to try turning off the lights and see if that works?
The problem is if I turn off the lights, you can't see your own notebooks.
What do you want to check if that actually works? Or like whether it would be.
We've tried it before.
Yeah, I thought we tried it. Well, that means this light is off. Now wait a second. If I put
I
this
think
light
all the
on.
electricity is attached.
No, I think
What did
this screen will go off.
Yes.
Yeah. Rutgers only.
Oh, wow, that's good they are there.
Wait,
I
and
see
then the light from
Oh,
back
it
then-
is
so much.
Oh, yeah. that works.
I don't know.
No, I because the light from that it lets us see
Sort
our
of
less-
illuminates, sort of.
I think this is better. I think we'll deal with this. We can read. I'll just read to you what it says. Do this. I don't know, orally.
I think that the camera may be too.
Let's move on. It's imperfect. We'll talk after about how to deal with this. What is this set? I want to know all the points so that after k, every single function is within 1 over n of the limit. Okay? So what happens to this sequence? So for fixed n, what's the difference between e n k versus e n k plus 1? E n k plus 1 only starts this restriction at k plus 1 and not at k. So this is less restrictive. So this is contained in this. Okay? So we have an increasing sequence of these e's. And what is the limit? What is the union over all of these? So I'm making it less and less restrictive while asking for this difference to be at most 1 over n.
For fixed time.
For fixed n, I'm fixing n. What is the set of x's?
Like all of E?
It's all of e because what we just said is that fk of x goes to f of x in e. And if it goes there, then eventually, after some, for any given x, we don't have uniform convergence. So for any given x, well, we do have convergence for any given x. For any given x, there's some value after which we're always within 1 over n. And this is capturing that value at some point, at every point x. So that's going to go all the way up to e. The measure is if e is finite. We have an increasing sequence. That means we can chop it at some point and be within epsilon of the limiting measure. So let's just write that out. Since the measure of E is finite, there exists, what do I want to call this? K sub n, such that the difference of the measure from E to, thank you. Oops, there goes the statement, but we know what it says. We want uniform, thank you, convergence on some closed set of large measure. So since the measure of E is finite, there is some point after which we are within, well, how good do we want this to be? You'll see in a second why we want to be within 1 over 2 to the n. I mean, it's clear what we're going to do with it. Well, maybe it's not entirely clear what we're going to do with it. But notice that, maybe it's clear what we're going to do with this. It's 1 over n. It's the same 1 over n no matter which x we're in. So that's our first hint towards uniformity. Right? Now, we have all these sets. We have one for each n. We're going to need something that works for all n. So let I'll call this A epsilon twiddle, because it's not yet necessarily closed. Let this be the intersection over all n. Let me think for a second. I want to choose, I'll tell you what capital N is in a second. I want to choose capital N in a certain way, and then take this intersection over these sets where capital N is large enough that the sum, well, it's just the sum of 1 over 2 to the n is at most epsilon. Epsilon over 3 or something, but let's not worry about that. In other words, I want to know that the sum of the tails of these measures is small, and that's the n and I want to take those tails. Okay? The sum of the differences to the tails is small, and I want to take those tails, all those tails. Okay? My claim is that the convergence on my claim is that on A epsilon, Fk converges to F uniformly. And notice what the difference from A epsilon to E is. It's at worst any of these. So it's at worst epsilon. So far, so good. Why is this true? Yeah?
Because you could just pick that capital N for all of them.
Exactly. That's what I'm trying to say. Let's say that precisely. I.e., what would it mean for the convergence to be uniform? I.e., what I want is that for every, I can't use epsilon now, let's call it eta, delta, epsilon prime. Are we so tied to the letters? All right, we can call it epsilon prime. For every epsilon prime, what would it mean to be uniform? For every epsilon prime, there exists some, let's call it n prime, such that for all k greater than n prime, fk of x minus f of x is at most epsilon prime. And that's for all independent of and for all x in a twiddle epsilon. Okay? This is what uniform convergence on this A epsilon means. It means we get to choose the epsilon without worrying. We get to choose this n independent of x. Question?
When you were making the ascending chain of the E sub nk's,
Yes.
you said that when you have k plus 1, that's less restrictive.
Well, I'm only asking about the functions fj with j bigger than k plus 1.
Sure.
And this is asking about the ones bigger than k plus 1 and also the kth one.
Right, okay.
So it's a smaller set.
Right.
Yeah.
Why is it again that the A epsilon twiddle is close to E in measure?
So the difference from E, this is the intersection of each of these. So the difference from E to A epsilon, maybe I should have written this explicitly. You can't see there. Okay, we remember what these E and Ks are. Let me slide this up like that. So note that the measure of E take away A epsilon twiddle, well, it's certainly at most, it's covered by all of these. It's at most the sum of the measures of E take away E n kn, where n ranges bigger than this capital N, that was determined by each of these having size 1 over 2 to the n, and capital N is the one, this sum is 2 to the minus n. So capital N is like log 1 over epsilon or something. Right? point is that this is at most epsilon.
Wait, could you say that again? Why is this less than epsilon?
So each of these
Yeah.
is at most 1 over 2 to the n.
Why? Yes, okay, gotcha. Okay, got it.
And the sum of them, the way we chose capital N was that the sum of them would be at most epsilon. Are you satisfied with that?
Where's that first inequality come from?
Yeah.
This one?
No, measure E without A.
Yeah,
so
from
that's
that
not
one to
full
that
on.
one.
Ah.
it's like, yeah.
These guys cover this. Because if you take E and you take away this thing, well, you could take, this is the intersection over all the E's.
Okay, yeah. I see.
Should I draw a picture?
No, I see.
No, it's okay. So this is the intersection of all of them. So anything in here will be definitely, so this set is a cover of this set.
Mhm.
That's right. Okay. So the point was we found a set, A epsilon, A twiddle epsilon. We're going to take a subset of it that's closed and has size at most, and difference, the amount that we're losing measures again epsilon at worst. So this set, which is not yet necessarily closed, differs from E by at most epsilon over 2 if you like. And on this set, I claim that the convergence is uniform. Okay? So, someone has given us an epsilon prime. We need to find a capital N prime so that this happens. But the A tilde, is the intersection of these ENs for N after capital N. So this will happen on any En with a 1 over N here. So just take N bigger than 1 over epsilon. Does that make sense? So proof, I'm proving this claim. Where's my claim? This claim. Proof of the claim. Given this epsilon prime, let N prime be 1 over epsilon prime, or be bigger than 1 over epsilon prime. Okay? Then, for all k bigger than N prime, what do we know about this? And for all x in A tilde epsilon, I guess I want N prime and N.
I think you want K of something.
Well, the Kn is the, yeah. If x is in A tilde epsilon, then it's in, that implies that x is in E n Kn for some n, greater than N prime.
Every.
Yes, in particular for some. And what that means, which implies that, the definition of being in this set is that you differ by at most 1 over n. The definition of being in this set is that fj of x, or fk of x minus f of x, differs by 1 over n, which is bounded by 1 over n prime, which is bounded by epsilon prime.
But this bound starts with Kn, right?
Yes, for all j greater than Kn.
But we need something like N prime.
Right, so n prime, let's see, let's get this right. N prime given greater than this and k sub capital N, something like that. Then the maximum of these. Let's see, what did I write down here? So given some epsilon prime, we want to find an n prime so that for all, well, we want to find an n prime so that for every x in here, this difference is at most epsilon. So x is in one of these a epsilons, a twiddle epsilon. That means it's in one of these. For an n, for a kn greater than n prime, is that better? For n greater than n prime and kn greater than n prime, since it's true for arbitrarily large. I mean, an is the intersection of all of these. So I can find one that's bigger than where the kn is bigger than n prime and n is bigger than n prime. Then for all j bigger than kn, which is bigger than n prime, I have this condition. Okay, is it clear?
Is k greater than log 1 by epsilon?
Is k,
N greater than log 1 by epsilon?
is n, oh, you
Kn.
an,
Kn.
kn, I don't have control on kn. I don't have control on kn. Let's look back at where kn came from. These sets en are increasing to e. And eventually, some kn has a small difference to e. So I don't have control on how long that takes. I just know that it does take some period of time. Oops. Okay, are we clear on this? Let's go over the proof one more time. So you give me some epsilon prime. I let n prime be bigger than, well, I don't even know that these kns are monotonic. I don't think I need this. Take that. Take just 1 over epsilon prime. For every k greater than n prime, so I want to take, n prime is fixed now. N prime is of size 1 over epsilon prime. It's fixed. Eventually, both n will be bigger than n prime and kn will be bigger than n prime. Okay? For any x in a epsilon tilde, it's in one of these with n and kn big enough. On each of those sets, this difference, for every j after a certain point, this difference is at most 1 over n, which is at most 1 over capital N prime, which is at most epsilon prime. That's uniform convergence. That's the definition of uniform convergence on the set A tilde epsilon.
So what about like between kn and n prime? Don't you technically need to get those points too?
So all I'm trying to say is that if any j,
Like it needs to hold for everything after n prime, not just starting at some point past n prime.
Yeah, I'm kind of going around in circles. I want n prime to be the place at which this kicks in.
Right.
And I want it to be of size 1 over epsilon.
Yes.
But I also want it to be related to this, the capital N of A. Let's think for a second. For every k, I want to be able to tell you where you need to start. So let's think about it this way. Where do you need to start? At which j do you need to start? Well, you need to start at j sub kn. Okay, the kn's are some increasing sequence, and I can add the extra condition that just increase them if need be so that they're monotonic. Okay, then I may as well start at 1 over epsilon or k sub big N. And as long as they're monotonic, then once n is bigger than capital N, kn is bigger than capital Kn, and then I know where to go.
So how do you get the points between kn and n prime?
There are no points between kn and n prime because this starts at kn,
Right. Got it.
and this is a bigger k, possibly bigger kn, so it certainly starts at n prime, at big N prime.
Yes. Okay.
Okay, so there's nothing in between. Good. Yes?
Why don't you replace little n with big N? And then just go from there.
Why don't I replace little n with big N? Well, yeah, I mean, I could. That if I'm on this thing, then I'm in E sub big N Kn, you're saying.
And then it's just shorten everything.
Well, no. What I want to know is that this difference is at most 1 over n prime.
Then let J just be greater than K sub n. Or K sub big N.
The
Sorry.
statement is, let's go over this again. This is subtle. The proof of the claim is that we have uniform convergence. There's so many epsilons and n's rolling around. That's what makes, I think, this argument a little subtle. Given epsilon prime, I need to know that this difference can be made at most epsilon prime for any epsilon prime. So I can't just set big N to be big N prime to be big N, because that will only guarantee me a size 1 over n, and n isn't moving. N determines the set 1 over epsilon. I need to be able to make this difference smaller and smaller and smaller without changing this set. This set is fixed. It has its own epsilon, it has its capital N.
Oh, you picked your big N.
The big N was picked here.
Sorry, N prime. I meant N prime.
The big N prime I get to choose.
Okay.
So all I do is I choose it to be at least 1 over epsilon and k sub big N.
Why the K sub big N?
The k sub big N is so that we don't run into trouble here. So the point is, if n is bigger than big N, and kn is bigger than big N prime, if n is bigger than big N prime, then I'm within epsilon. When does that kick in? It kicks in for any j bigger than kn, but that's bigger than n prime, again by creation of n prime. So there is no early stage where I might be off, where I have to wait for this to kick in.
I'll think.
Okay. It's subtle.
Yeah, it is.
There are a lot of moving pieces, but I think we nailed it. Okay, just takes a little bit of time and thought. All right, we're almost done, and what we need to finish is what we said already. We have this set A epsilon twiddle on which we have uniform convergence. There, by what we proved before. So A epsilon twiddle is not necessarily closed. But there exists an A epsilon, which is a closed subset with the measure of the difference at most epsilon. And you put the epsilons together, hence the measure of E take away A epsilon, which is closed, is at most epsilon. And we have uniform convergence on. Sorry, thank you. So what we proved before about any measurable set having a closed subset with set difference at most epsilon, now hit it to this A epsilon tilde. We had uniform convergence on A epsilon tilde, so of course we also have it on the subset. And this subset is closed and it has small size. Okay, that's Egorov's theorem. So let's look at the statement one more time. And the three principles. The statement is, if you have any sequence of measurable functions, bless you, on some measurable set with finite measure, we needed the finite measure to know that this convergence will imply convergence in measures. Assume that we have this convergence for almost every E, which is by trivially throwing out a set of measure 0 equivalent to every x in E. Then, for any epsilon, there is a closed subset of size almost the same, and the convergence is uniform on that size. Okay? So let's go over the proof. We sort of guessed, or we got a sequence of sets that have what looks like the desired property, observed that as k goes to infinity, we get the whole of E, and then did analysis.
Why did we have the closedness again?
It's nicer to have closed sets sometimes than not. I mean, why did we insist on this closedness?
Oh no,
In
what
the
I mean,
statement.
How did we get the closedness?
Oh, how did we get the closedness? That was at the very end, after we got our A tilde epsilon. There's a theorem that we had proved that any measurable set contains a closed set of measure difference epsilon. And this is like 2 epsilon, and then you change epsilon.
And while we're focused on the closeness.
Why do we want closedness in Egorov's theorem? You'll see that in the applications, it'll be convenient to be able to take this to be closed. So we could have just said there is some measurable subset on which this happens, and then when we go to use it, it'll be convenient to have a closed set, so we'll say, it's a choice of where do you want to do this last step, this last step of giving yourself a closed subset instead of an arbitrary subset. There's nothing deep there. The point is, for any measurable set on which some sequence converges, there's a subset of almost full measure on which it converges uniformly. That's the
It's to avoid like an application say, okay, go back to the proof, and at the end you see you can do this, and then like, okay, now we can.
Yeah, but it's actually modular, right? All we did is at the very end of the proof, we proved that it converges, that there's some set on which it converges, and at the very end we plugged in this modular piece. So we could have chosen to plug in that modular piece only when we needed it in the application. But historically, that is what Egorov proved, so I stated his theorem. Okay, so that was the third principle. Every convergent sequence is nearly uniformly so. What do I mean by that? Egorov's theorem. Let's get to the second principle, and then I will try to... I don't want to rush, but I do want to... I want to, in a not rushing way, cover a lot of stuff quickly. Okay, here's the second principle. What page is this? This is page 3. Okay, any questions on Egorov's theorem? Any questions on the proof? So now towards 2, let's prove Lusin's theorem. And I will try to remember that I'm supposed to write a little bit bigger. So again, every measurable function is nearly continuous. So let's prove that. Let f be measurable. Let f be, I had a notation, but never mind. Measurable on E and finite valued. And finite valued, just to make life simple, assume, again, that the measure of E is finite. Then, for every epsilon, there exists a closed subset, F epsilon, of E with measure difference at most epsilon, such that F restricted to Fe is continuous.
Could you move it to the left?
To the left. Sorry. Yeah, I zoomed in so much that now I don't have any room side to side. Let me move this to the left as well. Bless you. Okay, so one more time. If you have a measurable set on E with finite values and E itself has finite measure, then for every epsilon, you will find a closed subset with small measure such that F restricted to E is continuous. Sorry? F restricted to, thank you, F epsilon is continuous. I want to just note, and maybe you guys will explain to me why this is the case. Note, this does not imply that F restricted to E on all of E, in other words, not restricted at all, is continuous at all points of F epsilon. What's the difference between these two things? Yes?
You can take sequences in E minus F epsilon if you just restrict it to E, and those
Right.
could mess up your...
Right. Does everybody see that? So if this is E, if this is like my little set E, and this is my set F epsilon, and this is F epsilon, then if I'm trying to prove continuity, well, let's say I'm trying to prove continuity here. I mean, I've drawn it like it's intervals, but really it could be some crazy dense combination of the two, with f still being closed. But I don't want to be able to take limits in E. In E, it might not be continuous at that point. But only if I restrict the sequences to f epsilon am I guaranteed to have continuity at that point. Okay. That's what I want to prove. And you can't see what I'm saying. That's the second principle. Every measurable function is nearly continuous. Let's take this down and slide this. Okay, proof. All right. What we saw before is that by previous theorem, did I give it a name? Whatever it was. We had a theorem that there exists a sequence of step functions, now it is useful to use not simple functions but step functions, finite sums of rectangles, of characteristic functions of rectangles, linear combinations of characteristic functions of rectangles. So there's a set of step functions which converge to f for almost every x in E. Okay? Now, what do step functions look like? These are, again, finite linear combinations of rectangles. So you have a bunch of rectangles. They don't have to be disjoint. These are my RJ. Where are the discontinuities of the FNs? Yeah, the discontinuities are all happening here. Any place where you have these endpoints. So if you just pull an epsilon away from all the endpoints, take it like an epsilon thickening of the boundaries of all the rectangles, and remove those away. So for each Fn, there exists set En in E with, well, it doesn't have to be in E, actually. It's the set difference that we constructed that has small. So there's some set En with measure of the En at most 1/2 to the n.
And something satisfied not on En?
Sorry. For each Fn, there exists a set En with this measure on which Fn is continuous. Sorry. These are the ENs are the error sets. So these are my epsilon thickenings. So on which the complement, such that Fn restricted to the complement of the En is continuous. Okay? These indicator functions of rectangles are very nice. They're defined on all of RD. They're just 0 outside of some finite range. That's still 0 is a nice continuous function, believe it or not. Analytic even. Okay? So we have these we have this thickened set, which we're calling En, and we can make its size arbitrarily small, and in particular we can make it its size 1/2 to the n. Outside of those, this function Fn is continuous. Okay. Now, we have this convergence by Egorov. We just proved that there exists a closed set. There exists a epsilon closed subset of E, closed subset of E with, thank you. Egorov, there is a closed subset of E with measure at most epsilon, and the Fn's converging to F uniformly on this A epsilon. That's what we just proved. it's here that it'll be useful that this thing is closed. Well, only in the sense that in Lusin's theorem we want to prove that something is closed, but you'll see eventually where we want closed sets. Closed sets are nicer. Okay, so consider the set, what do I want to call this? Let's call it f prime. And again, there will be a set f, which will be the closed set that we want inside it. This is A epsilon. Take away the union over all of these bad ENs for n starting at capital N, where capital N is determined as before, where capital N satisfies the sum of 1 over 2 to the n bigger than capital N is at most epsilon. Epsilon over 2. Epsilon over 2. Question?
Are there any cases where there are step functions whose measure of discontinuity, or the set of discontinuity is measure greater than 0?
These are finite linear combinations of rectangles. So every rectangle, the measure of the discontinuity is 0.
So why don't we just use 0 instead of
You mean just remove these points? We want to give ourselves a little bit of room on which to have, because we're going to want, we will want uniform continuity. We're trying to prove that it's continuous. If I take away just these sets, well, if I take away a set of measure 0, it's not continuous. I want to have a little bit of room around which I'm not thinking about the continuity. In other words, from here to here it jumps from 0 to 1. So I want to have an epsilon to the left and the right, so that it's just 0, and then it's not defined. You can't do anything, and then here it's just 1. I don't want to be able to. I want to stay away from the discontinuity. So I want a little bit of room, but so much so that on this complement it's continuous.
Okay. It seems to me that you can do without the, like, whatever. It doesn't matter.
Yeah, you can take an arbitrarily small little thicket. Okay, so again, we're taking the set on which the fn's converge uniformly, and we're taking away the en's on which the fn's are not continuous. Okay? What's the set difference from f to en, a epsilon? So, then the set difference from a epsilon to f prime has size at most epsilon by construction, and the fn's are all continuous, on a closed set and converging uniformly on a epsilon, are continuous and converge uniformly, that means the limiting set continuous functions on converging uniformly converge to
Continue.
This is what we talked about on day 1, which implies f is continuous on f prime. Pretty easy. All right. So again, for each n bigger than n, this is, and for all n bigger than n, the fn's are continuous because we've taken away the place where they're not continuous, and they converge uniformly by construction. So f is continuous there, and the last step is as before. Now let f be a subset of f prime that's closed, and the measure of f prime, take away f, is at most epsilon. So we started with e, we dropped the set of measure at most epsilon to get to a epsilon, we dropped the set of measure at most epsilon to get f prime, we dropped the set of measure at most epsilon to get f. F is closed, F is continuous on F prime, so it's also continuous on F. Question?
Could you just explain the note once more?
The note.
Under the theorem.
The note under the theorem. This note under the theorem.
Yes.
This note under the
So
theorem.
you're saying that F's restriction on E is continuous, is
So,
not continuous.
What would it mean that F, so restricted to E just means not restricted to, at all. So I have this set F epsilon.
Sure.
It's not saying that F restricted to Fe, which means it's just undefined outside of Fe. That being continuous means you measure limits in Fe. Now, this, if F was continuous on all points of Fe, that would say if I have a point that's in Fe, and I take limits to the left and to the right, or nearby, we're in RD, so there's no left and right, but nearby points all have the same value, but nearby points could be taken from E, and not from F epsilon.
Oh, so you're talking, okay.
So this would say, it's not true that necessarily that F is continuous on all points of Fe. The function F restricted to Fe and undefined outside of Fe is continuous.
Right.
That's just the distinction. Okay. Any questions on Lusin's theorem? So again, if you have a measurable function, this is the second of Littlewood's 3 principles. If you have a measurable function away from some closed set of closed subset of difference measure of most epsilon, the restriction of F to that closed set is continuous. Yes?
I'm not understanding exactly how the capital ENs are being chosen.
Okay. How the capital ENs are being chosen. So each function is a simple function, is a step function. So I have a bunch of rectangles, a finite number of rectangles. And the step function is continuous outside some epsilon thickening of the boundary of those rectangles.
Epsilon thickening of the boundary, but it's the boundary of all those rectangles put together.
Yes.
Right? It's not like, oh, inside the intersection something.
No, just take all the if the linear combination at this rectangle, here it takes the value -1, and here it takes the value 2, and here it takes the value 3, well, here it takes the value 5.
Yeah.
So it jumps everywhere where there are horizontal and vertical and d-dimensional lines corresponding to coordinates of some rectangle. So if I take an epsilon thickening of that for some very small epsilon, when I add up all of those across the finite number of rectangles and all of their little lengths, I can make epsilon small enough that that measure is still at most 1/2 to the day. So I'm just getting a little elbow room. And the question is, do I really need that elbow room? Where in that elbow room am I using the argument? Well, I just want to keep distance from where its value was 0 and it jumped to -1, and here it jumped to 2, and here it jumped to 5, and there it jumped back to 3, and so on.
Where do you use the positive distance?
Where do I use the positive distance? Am I really just doing it for convenience? I mean, this is the kind of thing that, let's think about for a second. The convergence is uniform, and it's continuous. I mean, in a sense, it's this function, I mean, it is defined here, and you can take limits on both sides, and I don't want to be able to take limits on both sides. So, if I cut this away, well, I could take arbitrarily close points here, which would have some neighborhood around them that would... Yeah, that's not really true either. I'm not sure where I use it. Let me leave that as a something to think about. So, exercise. Do you really need this? Or could you just take literally the boundaries of the rectangles? I don't see immediately why we can't just take limits, the boundaries of all the rectangles, which has a measure 0.
I think I have.
Okay.
I worked it out without doing
Yes.
the lesson over doing. The way I did it was to note for each epsilon there's some set of discontinuities.
Yes.
Okay. Then I considered E remove the union of the set of discontinuities.
Yes.
right? That measure is still finite, and f sub n, all the f sub n are continuous when restricted to e prime,
Yes,
right? Now, by Egorov,
Egorov.
there exists a sub epsilon, which is closed in e prime, such that f sub n goes.
Yeah. So anyway, you end up removing it
But
because if what you want to remove is this boundary is a closed set. We have closed rectangles, and you're removing the interiors of the rectangles, for example, or you're leaving the interiors. What you're removing is the boundaries. The boundaries of the rectangles are closed sets.
yeah, there are also measures.
And they have measure 0. But when we take this closed subset of E
Yeah.
and we take away, so the fact that it's closed and, no, that's not true either. It's not true either. I'm just being safe, but maybe I'm being safer than I need to be. Maybe. I don't see at the moment why I can't just remove take a scalpel. I'm taking a little bit of a paintbrush, but I could take a
Because
scalpel.
Doesn't the theorem give you that it converges pointwise at almost every x anyway? So I guess you're using that, right?
This convergence.
Right, to strip away the boundary. Like you know that there are points where it's
Yeah.
continuous on a set of measures anyway.
Let's come back to this. Yeah?
I think I realize why it's important to remove.
Yes?
If you have your box, you could have it diverge up to infinity at near those boundaries, right?
Well,
So
but
you
each
have
of
to remove it.
It's a finite.
this is a finite sum.
Right.
Each Fn is a finite sum. But you're saying in the limit, I could get more and more of these things. But all right, let's come back. Let's come back to this issue. I have to think about it. I have to think about why I really cut that out. What I wanted to do in the last 4 minutes, no, 6 minutes, we're okay. We're not that okay. Is to, okay, what I have in mind to do is to redo everything, but I'm running a little low on time. What I want to do is redo everything from the point of view of abstract measure theory and prove Caratheodory's theorem, and then all of this, it'll be good review, but it'd actually be a new theorems, because they'll be the abstract versions of all the theorems that we've learned over RD.
So we're doing chapter 6 now?
Yeah, let's jump a little bit. We're going to jump around a little bit. Okay, so more general setup. Maybe I'll just have time to state some of the theorems, and we'll prove them next time. So X is some abstract set. Again, I'm not going to do Zermelo-Fraenkel axioms of set theory, but at some point you can't have definitions in mathematics. You can't define, if you read Euclid's Elements, a point is that which has no breadth, and a line is a set of points that lie evenly within it. What the hell is he talking about? The point is he's not talking. It's nonsense. And Hilbert comes back and says there must be non-defined things. So this will be, what you really define is what you do with things. So here's what you're allowed to do with this set X. First I want to define an algebra. An algebra, which is a terrible word because it means 1,000 things. An algebra A on X, in this case, is a set of subsets of X such that it's closed under, such that A is closed under complements and finite unions and finite intersections. Okay? That's an algebra. A premeasure, it's a definition, a premeasure, let's call it mu0 on X together with an algebra A, yes?
You only have A non-empty or contain 0 or X?
Yeah, let's make it non-empty. I mean, it's closed under complements and finite unions. So if I have E Well, I need to have
You
something,
have E or
and the empty set is in A. That's somebody in A, not empty. Yes. Okay, premeasure is a function from A to possibly 0, possibly infinity, such that I had better give the empty set is in A, I had better give the empty set a premeasure 0. I want it to be countably additive. And mu 0 is countably additive. So if E1 through En and so on are all in A, and I need to, and pairwise disjoint, and if the disjoint union, which I will call E, is an element of A, which is no longer guaranteed since A is only a algebra and not a sigma algebra, then I will want the premeasure, of E to be equal to, so this is countably additive, not subadditive, it's a premeasured countably additive, the sum of the premeasures. Okay? So premeasure is just a measure, but it's not on a sigma algebra, it's on an algebra. That's a premeasure. An outer measure, or exterior measure, it's an exterior measure, definition, an exterior or outer measure, mu star on X, it's a function from the power set of X, all subsets, is a function from the power set of X, all subsets of X, taking 0 or negative values, such that on the empty set, which it's allowed to measure, it takes measure 0. It's monotonic. In other words, mu star of E1 is at most mu star of E2 whenever E1 is contained in E2, and countably additive, and countably subadditive. So the measure of a union, not necessarily disjoint, is at most the sum of the exterior measures of the points. Okay, so an exterior measure or an outer measure doesn't need an algebra on which it's defined because it's defined on the entire power set. And the thing that it's missing is additivity. It has subadditivity but not additivity. And finally, I want to, okay, we know what a sigma algebra is. All right, fine. I'll state the Caratheodory theorems later. Basically, just to give you a heads up of what's going on, so we're going to set up pre-measures, mu 0. There's an extension theorem that turns pre-measures into exterior measures, outer measures. And then there's another theorem that'll restrict exterior measures to what's called Caratheodory measurable sets that will give us a measure, and this is a general process. So in our case, our pre-measures were rectangles. So it's A is the algebra of things that can be gotten by finite unions and finite unions of rectangles or their complements. And that the pre-measure is just the, what we were writing as absolute value measure. From that, we created exterior measure. We're going to do the same thing. From that, we restricted the exterior measure to certain sets that made it into measures. That's kind of the general theory. And when we do the general theory, it'll be a good overview because it's the same proofs as what we've already done for RD. So it'll be a good review of RD. This general stuff will not be on the midterm.